everyone to today's Beyond the Scope webinar. Today we're going to have our Assistant Director of Research and Development, Rob Williams, give a talk on the Titanate Themis microscopes, going over a lot of the capabilities there. So yeah, in addition to doing a lot of Assistant Director work with the research and development, he also manages these two microscopes. So he's kept quite busy on all that kind of stuff. And I just want to mention before we get started as well, the upcoming talks. So in 2 weeks, we'll have a cryo-EM discussion with Giovanna. So she'll be talking about how you're going to do some cryo-EM prep. So that'll be very interesting hearing about that, since she's been doing quite a bit of stuff on that at CMS in the time that she's been here. And then we'll be moving on to some low KV imaging in the SEMs with Steve Buna. I'll give this over to Rob for his talk. And if anyone has questions, problems, feel free. You can ask those in the Q&A, chat, all that kind of stuff. All right, Rob.
Good morning, everyone. Thank you for joining us today. My name is Robert Williams, as Dan just said. Today we're going to just talk about our Titan and our Themis microscopes. Both of them are aberration corrected, and I want to make this a somewhat general overview for people, so that if you're non-technical and watching, you have an idea of what's possible. If you're a grad student, you can think about what you can do with your research going forward, and then for PIs and industry, if you happen to see this, maybe spark some interest as to some cutting edge research we could do with these microscopes. As Dan said, please post any questions or problems you're having. And if you have any questions you want to stick around at the end, feel free to, and we can have a discussion. And if not, send me an email and I'll get back to you when we have time. A little bit about me. I went to Virginia Tech as an undergrad and got a BS and MSc there. Came here and did my MS and PhD. Did some postdoctoral work, and then had a small stint as a research assistant professor with University of North Texas. I came back here as senior research officer, and now, as Dan said, is working as the assistant director for research and development. I do quite a bit of outreach with industry, and then I enjoy these microscopes, so I try to make sure they're working in the best condition they can, and make sure that students are learning and becoming proficient. My research interests tend to stay metallurgical. They've become a little broader, but I like to try to correlate structure-property relationships by using quantitative electron microscopy. And then now, correlating electron microscopy with whatever type of electron, material problems we can, and identifying workflows for industry to help them solve their problems. They ask us to post something we like to do fun, and so I like to snowboard. Unfortunately, even with this environment, I'm not able to get out there and do anything this year. So looking at these pictures, I have to live vicariously through them, but good times. So something else we get to have that really is pretty much good times is our facility. I'm not going to talk about all the microscopes on here, but if you're not familiar with CMAS, I encourage you to take a look at the webpage, reach out. We have one of the most robust and best microscopy facilities in the world for the things that we do. And so, yeah, we're here to collaborate, and we like to call ourselves a collaboratory. So if you have research and you want to do it, reach out. We're looking for people. Today, we're going to talk about our image corrected and our probe corrected microscope, the Titan and the Themis Z. And, with COVID, we were uniquely situated to sort of continue providing the services that we have. And one of the reasons that we were in that situation is we built our facility to essentially run under remote microscopy conditions. And you can see in this picture that there's two students sitting to the left, and there's a microscope, this box off to the right. That is this is a Titan. You can see here Titan. This is what our Titan looks like. The microscope is built inside a box in order to protect it from the environment. And so the four main things we try to do is protect it from electromagnetic interference, mechanical vibrations, have a stable temperature to within 0.1 degrees Celsius, if possible or better. And then you need extremely clean power and quality and availability. So we built a facility that provided that. Thermo Fisher provides a box that is, its goal is to provide these protective services, but the box can't do enough. And so we put it in this room, and this room is another layer of protection. It's sitting on a pad. You can see a cut in the floor here. This pad is isolated. The temperature is maintained. That's what the curtains are for. Our box has electromagnetic coils around it in order to cancel out electrical fields. And then we have the building around this box, and the people sit outside the room. The people are the largest perturbation. So in that sense, we had developed a facility where we could broadcast our microscopes around the facility. And then with our direct connection to ORNet, we can broadcast them across the state of Ohio and now the world. So it works really well for us. But these environments are necessary for these two microscopes. And so the data you'll see today and the work you may want to do, part of what makes it really possible is the facility that we're in and the effort that was put into reducing the perturbations in the facility. So this slide has a lot of text. I apologize for that. I'm trying to list most everything that both the image corrected and the probe corrected system has, and there's a lot of overlap. Both systems come with an XFEG. This gives you a very high coherence and a high brightness source, which becomes extremely useful when you're trying to put a lot of electrons into a very small probe, which is what we do with these microscopes, whether in TEM mode or in STEM mode. Both systems come with a monochromator, part of what we'll talk about later today, which allows us to reduce the energy spread in the beam to under 100 millielectron volts, or around 100 millielectron volts. That's the same energy resolution that you have in a synchrotron. And so if you're familiar with X-ray analysis or near-edge structure analysis, you can do that same type of analyses in the TEM now, except you can do it with nanometer scale resolution. And so that's a game-changing event for people that want to look at structure and bonding and see that with spatial resolution. Because in a synchrotron, you have very little to no spatial resolution. And so you're just looking at large areas, so you can't just discretize small areas. Both systems are variable voltage. They go from 60 to 300 kV. The Themis actually can go down to 30 kV. The STEM resolution in the Titan is 130 picometers. That's extremely good. But when you look at our probe corrected Themis Z, you see where probe correction really plays a role. We can do better than twice that in our probe corrected Themis Z. The other real step up in technology in our Themis Z is Ulti-Mono. Ulti-Mono gives us another level of energy resolution that lets us get down to around 30 millielectron volts. So this opens a door for vibrational spectroscopy and plasmonic spectroscopy, if that's your T. What's one thing that's nice about these microscopes is that they have a relatively large pole piece for the resolution that they provide. And so that allows you to tilt your sample and do analytical work, which is really helpful for most of the people we have here, because, or a lot of the people we have here work on crystalline samples or inorganic samples that are metallic or oxide in nature. So they need to be able to tilt. The systems both come equipped with Super XEDS. We'll talk about that in more in depth, but that's a quad silicon detector, a quad silicon drift detector that allows for very fast acquisition and efficiency in your X-ray collection. Both systems come with a GaN dual Eel spectrometer, and the Titan we actually have equipped with a K2 direct electron detector, which is also a game changer in the Eels field, and we'll talk about that a little bit further in the talk. If you were able to attend my previous talk, we talked in depth about the 4-segment annular detector and IMPAD detector. I'll hit on those today just for a slide, but I would call you back to those. But they have a large role to play going forward in materials analysis to help us imaging light elements in the systems. So just briefly, for those that deal with TEM, we have STEM on the left, which is in the Themis Z. We're going to converge a probe down to a point and look at the diffracted beam through the sample and collect various diffracted signals, as you can see with these detectors. I'll show a couple of the images that you can get and you can expect for this. What's really nice about STEM, and why typically most of what you see today is STEM, is that with the improvement in scan engines and the improvement in optics, we can form a probe that is sub-angstrom and scan that over our sample and collect multiple signals simultaneously. And that signal is considered to be directly interpretable. And what I mean by that is that where we see a bright spot, we expect an atom to be, or an atomic column to be. In the TEM, or the Titan, over here in the middle, that's not always the case. So if you are a little bit older and have read the literature, anything before 1995 or 2000 that you saw was pretty much all HRTM. Anytime you saw any type of atomic resolution image, that's what it would be. HRTM is not directly interpretable. HRTM is a phase contrast image where the contrast in the image and the atomic position is dependent on a few different variables, some of which are defocus and thickness. And so there were ways to go through and produce directly interpretable images, but the stability of your sample and the system really made those things very difficult to believe. So we'll talk about a little bit of the images that you can get out of this and the power that they bring. But then I want to talk a little bit at the end about the spectroscopy and the signals that come when the beam interacts with the sample, and what we can gain from that. So the X-rays and then electron energy loss. So not a lot of people do HRTM anymore based on sort of the points I was just making. But I don't want to make it sound like HRTM has no place. It's just that people don't do it as much because it's more difficult. And they probably aren't working in the right materials for it. So we happen to have a world expert in it. He used to work for FEI company, which is now Thermo Fisher, or was acquired by Thermo Fisher. Jorg is a assistant professor in our department. And if you have HRTM needs, I direct you to him, because he is one of the best people in the world at doing this and has done excellent work. And what I'm showing here to the left is single layer and double layer graphene. And so where you find that this technique works really well is in extremely thin samples. So like I said earlier, the column position is determined by defocus and thickness. And if you have a 2D material, your thickness is as thin as possible. And it's easy to be at the right focus because there's really only one focus to be at and make it correct. So what Jorg did here is do image simulations and then also experimental images. And that's really where people tend to not go down the HRTM path, is that in order to interpret these images or display them as real images, you need to show image simulations. And so there's creating the sample and taking the images, which is very difficult, is only 50% of the work or 40% of the work. You need to then also do the simulations to go with it and have super thin samples. So this is very powerful in 2D materials. And it's also really good in nanoparticle work, right? So if you're doing things with catalysis or single particles, but I would recommend you contact us or contact Jorg directly. He's an excellent resource for this. Now in our Themis, we have a probe corrector. And if you read through the literature, you'll see different types of letter and core. And what S core stands for, I actually don't know. But what they stood for before were C core and D core. And C core referred to the fact that you were correcting your CS, and it corrected out to your third order aberration. And then D core was the fact that we were now going from using quadrupoles up to dodecapoles. And D core was a little bit of a misnomer because we didn't really have true dodecapoles in the corrector. Now in the S core, we actually have true dodecapoles and I believe other technological advancements. And without, going into that little rabbit hole, what this provides us is the ability to correct our aberrations out to the fifth order. And, for those optics people on here, how impressive that is. But what that practically gives us is the ability to have a flat phase field that is 51 milliradians. So that gives us an increased semi-convergence angle out to 50 milliradians from where in the D core we could only have about a 30 milliradian convergence angle. So now when you can have a 50 milliradian convergence angle that's aberration free, that allows us to get essentially the smallest converged STEM probe we can. And by doing that, we now have the ability to have a sub-angstrom probe, a 60 picometer probe essentially, that we can have anywhere from 60 up to 300 kV. And in doing that, you have the ability now to image moly disulfide, and you can very clearly see the dimeric structure and the separation between the dimers. So this is a beautiful image. It's also a beautiful sample. So to me, now that I use the microscope is the easy part. We have a microscope that can produce this quality image. What we have to do is produce a sample that can produce this quality image, and that's a much more difficult ask. And so we are very good at it in some materials, but if we're not, we're happy to work with you and try to get towards that point. Now, if we look at this in another material like strontium titanate, the contrast in this image is proportional to Z squared. And this is great to know because we want more than just a pretty image. So that means we can look at this and we can say that this atom is probably strontium and this one is probably titanium. But when you look at this, we have strontium, titanium, and oxygen. So where's the oxygen? And that's a little more difficult to resolve in HADF STEM. And we'll talk about later how we do that. But if you're interested in structural defects and seeing how well you grew, a CVD layer or a PVD layer or a atomic layer deposition, here's a strontium titanate substrate that's been grown, and the growers thought they had a pretty uniform homogeneous film that was epitaxial. And if you look at this, it looks rather epitaxial. But now from this image alone, we can start to see an extra dislocation plane. We can draw in edge on dislocations here. And if we're really precise and blow this image up, you can easily draw a Berger's vector around this. If you're a metallurgist, this is something you probably did as an undergrad in dislocation class. It's absolutely amazing that we can see something of this quality. You can also start to see distortions in the unit cells, right? So strain measurements could start to be made there based off of atom displacements. All sorts of things can come out of this image. And that's really where we're at, in microscopy, is how much more can we get out? What's going on in these dark regions where we're not seeing atoms? What type of strain is present around the dislocation? Does the dark region relieve the strain somehow? Where's the oxygen? So previously I showed you how you could do this and use segmented detectors to help you answer some of these questions. We have multiple imaging detectors, not just the segmented detectors that can help with that. And then we have spectroscopy. And so I want to open or talk much more about spectroscopy, but I'll hit briefly on these imaging detectors that we can use, and then go into super EDS and Eels. So last time we talked about this, but so if I have an HADF STEM image and I want to know where the oxygen is, it's not there. I mean, I know from the unit cell that it's here, but I don't see the positions. Well, with IDPC, we can see the atomic positions for oxygen very clearly, right? So if you had octahedral tilts or you're trying to look for that, this would be a way that you could image it and start to map it. Here in ABF, which is called annular bright field STEM, the same thing. We can see the strontium and the titanium positions rather clearly, but we also have the oxygen positions. So this is two ways now with the Themis that we can begin to image oxygen directly in the microscope. And this, 5 years ago, this would have been unprecedented. So truly cutting edge, and something that not many people have access to or have had the opportunity to take advantage of. So again, if this is something going on in your research, I encourage you to reach out. Another aspect of both of these microscopes that can be a little frustrating sometimes if you're actually working on the microscope is that they have a C3 lens. And so again, if you've used TMs, everyone should know about the C2 lens. It's the probe forming optic. In this microscope, we have an additional lens below that, the C3. And that gives you quite a bit of functionality and flexibility from an analytical standpoint. In STEM mode, it allows you to vary the convergence angle. So in STEM mode, we can make our convergence angle what we want it to be. You're not geometrically limited by the apertures in your system. So as you do analytical work, you'll know that's an extremely important parameter. And optically, you can go to a smaller aperture and then use the C3 lens to virtually increase your convergence angle such that you have this improved energy resolution or whatever you need while having a larger convergence angle. It also allows you the inverse ability to spread the beam out. And the way we use that is that we can use the C2 lens to converge the beam down to a small probe. And then we use the C3 lens to stretch it out so that it becomes parallel. And so now we have basically a scanning TEM probe. And what we call that is nanodiffraction, or a nanodiffracted beam. And that becomes extremely powerful because what we like in STEM and what we're trying to do is scan our probe over the sample and collect some type of data, spectra, diffraction pattern that we can post-process later and get more information out of. And we can do that now with diffraction patterns. So as you see in this image, we have spot diffraction patterns as the beam goes through this sample. And so as you go from a nice cubic crystalline lattice, you have a cube zone, just a slightly disordered region where now you just have twofold symmetry. Now we come over here into a completely disordered region and you see what looks to be a spot pattern, right? So now you can scan over your sample, and if you have small amounts of short range order or disorder, you can start to characterize that. And Dr. Wong, Jinwoo Wong, is a faculty member here who's really pushing this area of the field. And we call it fluctuation electron microscopy. But if you're interested in bulk metallic glasses or polymeric films that'll have, short range order or medium range order, this becomes a way to probe that. And so here, this is an image where you're selecting a certain diffracting vector and you're showing where the bright spots are, that you have a certain amount of short range order with a given vector associated with it. And for things like flexible phones or bendable phones and amorphous films, this type of research is really going to help this type of experimental work will help researchers understand what they're producing. Now, again, I talked about this last time, and we have our talks recorded, so you can go back and look at this, but we have segmented detectors in the microscope, and you saw the power of IDPC to image late elements. We can actually image hydrogen now in a titanium hydride. We've shown that that's possible. But there's many more things going on. You also have the ability to do magnetic imaging. And that's something that we're starting to push forward with Dave McComb and his research group and a few other people. So the 4-quadrant detectors are great. We also have the IMPAD pixelated detector, which has a list of possibilities here. And so you can use that for DPC and IDPC. You can use it to basically do dark field imaging and dislocation analysis. You can use it for diffraction contrast imaging. You can use it for pack bed and strain mapping. All of these things are available and here for use on our Themis. I should say right now the IMPAD is on the Titan, but in the near future, somewhere in the next 1 to 2 months, there's a good chance that we'll be moving that over to the Themis, which is where its final resting spot will be in order to get the most use out of it. So if we move on to some spectroscopy talk here, I want to talk about the Super XEDX system. And so most of you, especially if you're a young grad student now, you're probably familiar with silicon drift detectors. We have them on every system in the facility now. When we got our Titan, that was the first system to have silicon drift detectors. And what silicon drift detectors do and afford us is the ability to collect in this system, 500,000 counts per second. Now, previous generation silicon lithium detectors that we would use could only count 3,000 counts per second before saturation. So if you have a sample that can produce 500,000 counts per second, which if we typically have a thin sample in the TEM, you aren't going to produce 500,000 counts per second because your sample's too thin. You don't have enough volume to excite enough X-rays. But what you have with these detectors is an extremely high efficiency and collection angle. So you can see here in the schematic, we have our TEM rod holder, and you have these 4 detectors. These 4 detectors sit so close that they basically fill a solid steradium. And what that means is effectively we can capture, well, I won't say we capture all the X-rays because we don't. We capture a very large portion of the X-rays. And so what that means is if you have a thin sample and it's not producing a lot of X-rays, we're collecting as many of them as we can. And then these detectors are not saturating. And so you're still getting the best signal you can get out of your material. So if you work in metals and you have something 150 nanometers thick, you might see 500,000 counts per second. And in cases like that, if that's adequate for you, all of a sudden you can do a 5-minute EDS map and probably have enough counts to do 3 sigma certainty quantification. What's really nice about these systems is when you have these 4 detectors, you can see here if the sample rod is tilted, it's going to shade the detector. So the X-ray signal is not going to be uniform on all 4 detectors. And this will change how you should quantify and what your background should be. Thermo Fisher has done a really nice job of going through this and calibrating and determining proper absorption metrics for the different detectors based off of the tilt. You can actually even get separate signals from the 4 different detectors so that if you want to get rid of one because you think it was just noisy and not producing any real signal, you can do that as well. But all of this is contained in their newest software, VLOX, and it really is a nice EDS quantification and analysis package if you're looking to do that type of work. And when I talk about the efficiency of the detection, these are windowless detectors. And so you can pick up light elements very easily or much more readily than you would have been able to before on silicon lithium detectors. And so here we have organic photovoltaic, and it's 2 different basically polymer layers that have different amounts of carbon. One is a carbon C60 layer and one's a copper phthalocyanine layer. And in these 2 layers, you have about a 25 and a 75% carbon mass. And through EDS, we were actually able to, 75 and 65, but irregardless, through EDS, we were able to quantify that difference, which is just truly amazing. I guess if you've never seen that or worked in the field for a while, but the thought that you could off of a 20 nanometer thick layer, we could do EDS from a fib foil and quantify where the interface is based off of carbon concentration. It's really, it was impressive to us, I should say. And if you have an inorganic material like a nickel-based superalloy, here you can take a beautiful STEM image and show that there's bright elements segregating to something. And we know that there's a twin boundary here. But to look at this and be able to do chemical analyses, and in this case, atomic resolution EDS, here we can show where the nickel, the aluminum, the titanium, the tantalum, right, all the elemental species sit. And this allowed us to quantify what was sitting on various atomic sites and correspond this to the eta phase. And what we found was that eta phase was forming on this site, on this twin boundary, which was inhibiting creep. And so in developing next generation aerospace alloys, we want to reduce the weight of these. You may have heard in aerospace alloys that a lot of them have rare earth elements, and these rare earth elements are heavy. And now, not that tantalum and tungsten and niobium are the lightest things in the world, but we have to, we have, it's a balance of properties. You know, you can't just use the lightest elements and produce the strongest material. At least we don't know how to yet. And so these are still reducing the weight. And I think the number is somewhere, if you reduce the weight of an engine by 1 pound, you can reduce the fuel consumption by $1 billion a year. And for getting the monetary intake, it's about the carbon consumption, right? This is all about how do we reduce carbon consumption in aerospace. And so we're trying to reduce the weight. And this is a strengthening mechanism that helps make these alloys strong at high temperatures. And then you can show this. So the other type of spectroscopy in our microscopes is Eels. And you can think of this almost as the, well, kind of as the inverse of X-ray, right? So we fire electrons out of our gun at a very specific energy. We know what the voltage is. And they go through the sample. And when they hit the sample, they can produce X-rays, right? And how does that happen? The electron hits an electronic shell or an electron and excites it to a higher electronic shell, and it decays, and out comes an X-ray. Well, that electron that we fired out of the gun had a certain energy, and it had put some of that energy into the sample to produce the X-ray. If we have a spectrometer at the end of the sample chamber, we can collect the electrons that we fired out of the gun, and we know what the starting energy was. And if we can very precisely measure the finishing energy, we can measure the energy loss. And that energy loss is almost, it can be thought of as reciprocal in nature, almost to X-ray, right? So these are complementary, if you will, techniques. And on the, I mentioned this earlier, on the Titan, well, in both systems, we have high resolution dual Eels. Dual Eels allows us to do a quantitative Eels analysis. And without going into what that means, if you just take my word at it, both systems have that ability. Titan 2 has a K2 director, a K2 direct electron detector. This really is a game changer in the field of Eels. It opens up the energy range with which we can look at spectral energies or characteristic energies, and it maintains the same resolution basically that we had before. So now we can do spectral imaging and mapping like we would do in EDS, but do it using Eels. And Eels will show us more information about the bonding and the chemistry of the material, and can be quantitative down to single atom if the sample's thin enough. And what I mean by the K2 provides a larger energy window, I try to show it here in the slide. We're looking at carbon, nitrogen, and oxygen. And if you look at your energy scale, we go from about 210 EV to 580 EV. And this is collected with a 0.1 EV dispersion. So the 0.1 EV dispersion is the amount of energy that goes into a given pixel on the camera. So the K2 is a much larger camera and has a much larger number of pixels. And what that allows us to see is this large energy window of, what is it, about 400 EV. So when you're on the US 1000 or the GIF, which is what we would traditionally do Eels on and what we have our high resolution dual Eels on, here are the width of the spectra at 0.1 EV, these colored spectra. So if I want to look at carbon, nitrogen, and oxygen in a sample, I have to collect 3 separate scans in order to do that on the US 1000 or the GIF. With the K2, 1 scan suffices. And this is using the 0.1 EV dispersion. If you use the 0.5 EV dispersion, the energy window for the K2 goes up to 1800 EV. So what this means is for samples like strontium titanate, strontium's characteristic edge, the L23 edge, is going to be out at like 1900 EV. So now we have oxygen here at 500, Titanium would be around 480. We could put from 400 all the way out to 2200 on the spectrometer and be able to see strontium, titanium, and oxygen simultaneously while also mapping. And this is an example of that. This is really nice work from Jülich or from Chengli Zhao out of Jülich. Here, he's just using a 1 EV beam because we're doing a 1 EV probe. So there's no monochromation to this, just the XFEG as is. And mapping this, you can see the pixel density, but you can immediately resolve the titanium edge, the barium edge, the strontium edge, and the oxygen edge falls in. And the real strength of this technique is that, note, it's a 49 by 49 pixel scan, and it took 90 seconds or less than 90 seconds. One, we're worried about beam damage or dose. So to go faster means we're locally dosing the sample less. That's a plus. Two, we're worried about sample movement or instabilities. So the faster we can go, typically the better luck we're going to have in keeping a nice aligned image. And you can see here at this scan rate and these parameters, the sample doesn't look to have drifted in X or Y at all. So for Eels research, this really opens up the window for what we can do. And it's much faster. This scan took 90 seconds. If you did this with EDS, you might not be able to collect it. And if you did, it would take a longer period of time. And note, this is available on our Titan 2. This is not the probe corrected system. This is the image corrected system. So this type of resolution is coming out of a image corrected system. Now we've talked about the monochromator and what that can provide as far as reducing the energy spread. But the way we do that, is we have an electrical and a magnetic field that we use with the Veen filter. And these colored arrows are representing different beam energies. So you could think of the pink arrow as being 299.9999 volts, and this red arrow over here as being 300.0001 volts, and the spread between it. And if we can use the electric field to spread this out so that it's dispersed on the screen, as you see down here, this is what it would look like on a phosphorus screen. We then have the ability to put a physical aperture or a slit in that'll cut off this energy spread, right? And this energy spread is what contributes to, or one of the things that contributes to chromatic aberration in the microscope. So having electrons at different energies means that they're going to be focused to different points, right? That's just how electron optics work. And so by reducing the energy spread in the beam, that's another step we could take to increase the energy resolution or the spatial resolution in the microscope. So by doing this, we're not only reducing the energy, the electron and the energy spread, but we're also improving the spatial resolution a little bit because we're reducing the chromatic aberration. This is actually just a little schematic from back in the day of the actual monochromator. This is what's in the microscope. This is a little Lego man, so you can see the size of it, and the beam comes from down here through this little hole. And what it provides us is that if we look at this little plot here, the green line on the outside is your XFEG. That's what's in the microscope, and that's what, if you do Eels or look at the energy resolution, you have inherently. You have about a 1 EV energy spread. That may be surprising if you're used to working on a Techni, because a standard FEG or an SFEG that's in a Techni, that'll have about a 0.5 EV dispersion inherent to it. And so you would think, well, why doesn't the XFEG have a better energy dispersion? And the answer is because they wanted to have a high coherency, high brightness source. And the energy dispersion, unfortunately, had to be compromised. But it's okay because, again, you have the monochromator. And now what you see here in this blue filled is what we get with the monochromator excited. That's that's about a 200 millielectron volt full width half max. That's the spec of the microscope. Now in our systems, we actually can achieve better than spec, and both systems achieve around 100 millielectron volts without very much effort. It's rather straightforward to get to. So that's really powerful again now with spectrum imaging, because you can look at changes in near edge structure. And if that doesn't mean anything to you, I want to show you these spectra so that maybe that can resonate a little better. If we look at carbon and you think about diamond and graphite, and obviously people talk about graphene now, but we can think about highly ordered pyrolytic graphite, which comes out of like rocket nozzles and volcanic ash. Carbon orders differently, right? You can see here that there's very known different carbon ordering. If you have diamond or graphite or amorphous carbon, the pi star and the sigma star bonding is different. We can resonate those bonds in Eels and resolve changes in the pi star and the sigma star bonding. So here, this energy resolution is 0.45 EV, right? So that's the energy resolution that we have in a Techni, basically an SFEG. You can clearly see the pi star peak, and you can clearly see the sigma star, and you even see shape in this, right? Because you have 0.45 EV resolution. But if we look at this pink area is where some bonding is expected to occur, and you can see in synchrotron data, but we don't see in Eels data. Well, when you monochromate this is from STXM. That's a scanning transmission X-ray microscopy. So this is not Eels data, but with work I'm doing right now with Exxon, we can show this level of resolution on our Titan microscope. And so the pink areas are similar, or not similar, they are the same width, right? We're looking at a 5 EV energy window. And now look at all the features that appear in that 5 EV energy window that are not present when you have a 0.45 EV beam, right? So opening this up now, having this type of ability to look at bonding, to combine this with DFT calculations and simulations, it really is changing the way we can do material characterization on fine scale. Now, if we go to the Themis, where we have ulti-mono, this is really the next step in monochromation. And you may see some work out of the neon microscopes or super STEM. They have 10 millielectron volts, and they're doing some plasmonic work and some vibrational spectroscopy work using the scanning transmission electron microscope. We are pushing those edges now. So what we have in our system, we can achieve about a 30 millielectron volt beam. And to give you a feel for what that looks like, right? This outer one is again 1 EV. This middle one is 2 EV, 0.2 EV, which is what we just showed as the improvement and what's standard on both our systems. And now if we do ulti-mono, we can get something that is almost, well, an order of magnitude smaller. So if these are of interest to you, or you do any plasmonics research or vibrational work, we would be very interested to talk about setting up some work and experiments that could test these parameters. Let me also, for full disclosure here, you don't have a lot of current. So when you have monochromated the beam to this extent and reduced the energy spread, you've basically thrown away all your electrons. We made the joke at first that, well, if you only have one electron, you can't have very much energy spread. So it's not quite that bad, but there are very few electrons when you have that little energy spread. So it changes your experimental setup and what's possible, because the signal to noise is lower. But it still gives us potential to do some really cutting edge and game-changing work. So rather exciting. So some takeaways from this talk and overview is having both an image corrected and a probe corrected system in the same facility really provides great flexibility to provide the best characterization for your materials. You can, if you realize that you can't get something out of one microscope, you probably can get it out of the other, and it's just simply a matter of changing your sample over to that microscope. The combination of Super X and Eels really provides an unmatched ability to characterize chemistry and bonding on a nanometer scale. These two systems, it's just been really a pleasure to see how they've improved over the years, the data that can come out of them. And they work extremely well in our facility because of the environmental conditions and the efforts put forth by quite a bit of the CMAS team. And so we are collaboratory. We really want to work with you. If anything you've seen is of interest or you have any questions, please reach out, and yeah, we'd be happy to chat. So with that, I'll take any questions. Or
Thanks, Rob, for the talk. So yeah, if anyone has any questions, we still have a little bit of time to talk about the microscopes. There was a lot there, so probably interested in different areas as well. So feel free to post those in the Q&A is the easiest place for us to find those, or also in the chat if you're having any problems. Or if you want to ask any more in-depth questions, you can also raise your hand and we can unmute you for a little bit.
we also have a nice group of faculty at OSU, right? And so they're working and doing research in these areas and have graduate students in these areas. So again, if you don't have to, raise your hand right now, but feel free to send an email. You can reach out to me or directly to one of the faculty members if something overlaps or you think that you might want to do some research with them. Can I see the questions, Dan, or chat? There's something in the chat.
I haven't seen any questions come in yet.
Okay. I was just making sure that I wasn't missing. We had a good turnout for just the introduction. So I'm looking at the participants. I'm not actually, I don't think I know most of you. So it's, in all sincerity, feel free to ask a question if anything was unclear or you have any, so. I also, okay.
I was just going to ask about upcoming technology that, well, so what we don't have, we probably aren't getting anything anytime soon because we just got the Themis and whatnot, but other technology advances that have been going on in the TEM world.
Other than what I just said?
Yeah. Some maybe not capabilities that we have at CMAS, but just other things that are around and interesting.
Well, no, there certainly are a few. Probably you might take and say that cryo-electron microscopy and all of the things we're also showing from that aspect are really the next frontier. So that is certainly new. Everything going on in cryo and single particle analysis and the way we're pulling out information on a smaller and smaller scale from proteins and biological materials is new. Holography is one of the things I would say that we're really trying to do on the inorganic side, which is it enables you to pull out the phase and the structure of the material. So the idea of what I was saying in HRTM not being a directly interpretable image, if you can perform holography with it, it allows it to become a directly interpretable image. And so you then can combine that with holography also holography allows you to also do Lorentz magnetic imaging. So now you can do atomic resolution imaging with magnetic imaging. And so there's some pushes on that front. But there's still a real need, we can produce really, really good data. What we need is to better understand our data and process our data to a certain extent. So when you look at one of these columns, what we want to be able to do is tell you what the composition of the column is. But unfortunately, we don't know how to deconvolute out all the signals, even in Eels and EDS yet, to really, we've put error bars on it, but we'd like to reduce those error bars. So there's just some real theoretical work in understanding, I think, the microscope as opposed to technological advancements that need to come. But I said this in the last talk. The other big thing that'll happen, I think, is the MPAD detector, the pixelated detectors. They will increase in pixel dimensions. They will increase in speed. And you could see yourself in 5 to 10 years is that's the only detector you need in the microscope. And what you really need is a fast computer processing all the spectra and all the data, or the diffraction patterns and data coming out of the microscope, very similar to what we have on the cryo systems that are becoming automated.